So good afternoon, everybody. Before starting, let me say that it's a particular pleasure to me to give this presentation here because it's the place where I work, where actually I also studied. And probably last time I gave a talk here was in the graduation day, so long time ago. So nice to come back somehow. This presentation, as Tom was saying, deals with irrigation from the hydrological point of view, because irrigation is the most impactful human activity on the water cycle. But despite this, so despite the large amount of water that we move somehow, it's not so well monitored or not monitored at all. I also give this presentation on behalf of many other colleagues contributing, my research group, Luca, which is not here now, but people from Siena IRPI and many others. So let's start with the question, why irrigation? I already anticipated this, but the water cycle is changed. And we should adapt even the way we represent the water cycle, and we are already doing so. This is, for instance, a new diagram released by European Space Agency. The USGS did the same a couple of years ago. So basically, from the physical point of view, the processes are still there, the same, but there is something more, that is us, humans, that we use a lot of water for several purposes. And among the ways we exploit water, irrigation is for sure the most impactful one. So it's the source for which the largest amounts of water are used. Despite this, we don't have explicit and detailed data about irrigation dynamics. When I mean dynamics, I'm talking about knowing when and where irrigation occurs, and more important, knowing how much water is used for this purpose. So these are key questions that are the drivers of the research line, whose results are presented in the next few slides. How we try to estimate, to derive this information through satellites, because satellites offer the possibility of having a kind of remote eye that monitors both. It's not working. It's because of Luca. It's working. Okay. Okay. A kind of remote eye that can monitor both natural processes and anthropogenic ones. All the results that will be presented in the next slides are the output of a path, of course. And here there are just few milestones. Let me say that many of these activities, almost all of them, have been fostered by several research projects, mainly funded by the European Space Agency, that gave a strong impulse to this research line. And what I will present you is basically an algorithm we developed to map irrigation, so irrigation mapping, detection in space of where irrigation occurs, that is the CMAP method, and also an irrigation quantification approach, the soil moisture-based inversion approach that allows us to estimate the water volumes. So let's start with the mapping method. We have this method, which is called CMAP, Temporal Stability Indices Derived Irrigation Mapping. So it's a framework in which we use statistical features from the temporal stability theory, which was originally developed for another reason, actually, to optimize the monitoring of in situ soil moisture probes. But we use the statistical features used in that theory to map irrigation. How? We started doing this stuff with satellite soil moisture. So imagine that we have a data set of soil moisture observation from satellites in time, and that we have the soil moisture value in one specific pixel for one observation day. We compute two main indices that are the relative differences that quantify how much the value of that pixel differs from the spatial mean. And then we calculate also the temporal anomaly, that basically is how much it differs from the temporal mean, from its own temporal mean. We give these features as an input to a k-means clustering algorithm that restitutes the irrigation and non-irrigation clusters. Basically, pixels with higher values of both indices are wetter than the average and with respect to their temporal mean, so likely they are irrigated, and the opposite. Important thing is that this method is it's simple and easy to use and flexible. Flexible because it can be used with any kind of input data, which is a proxy of irrigation. So not only soil moisture, also for instance vegetation indices. And this is a result for example that we produced last year over the Ebro Basin that we saw this morning in the talk about drought. We used the Copernicus NDVI product at 1 kilometer to map irrigation and non-irrigated and non-irrigated areas over the Ebro Basin at 1 kilometer. We compared with reference information, obtaining an overall accuracy of 75% at the whole basin scale and more than 90% in this smaller area, which is it's very heavily irrigated, is where most of the irrigation occurs, and for which we have also better ground truth data. So we even for a smaller area, but with better, more reliable ground truth data, we have an higher accuracy. As I was introducing, the method is flexible. So for instance, this is another example of a work of 2022 in which we mapped irrigation at 100-meter resolution in central Italy. In this case, we exploited a soil moisture product based on Sentinel-1 and Sentinel-2, the S2MP product, which is developed by French colleagues. Coming to the irrigation quantification, we have this algorithm, the soil moisture-based inversion approach, that relies on the inversion of the soil-water balance. So we implement the soil-water balance of the first layer of the soil that we can sense with remote sensing, especially soil moisture, which is our main input. We based on the assumptions that over agricultural areas, the input water into the soil, it can be rainfall or irrigation. So what we do, we invert the signal of soil moisture to backwards estimate the total amount of water entering into the soil and determining that signal that we observe. In principle, when this is due to both rainfall and irrigation, if we remove rainfall from the output as a residual, we obtain irrigation. And this is the rationale of the method. So we write the soil-water balance. Each term is written as a function of soil moisture. I will not go too deep into the mathematics, but at the end, we obtain the total amount of water entering into the soil, which is our output. We remove rainfall, and as a residual, we obtain irrigation. With this algorithm, we developed the first ever irrigation water use datasets. So it's not irrigation requirement, it's irrigation water use. So actually, in principle, how much water has been delivered to the fields. These are 1 kilometer products over the Ebro Basin, Spain, and Po Valley, Italy. They cover the period, the more updated version from 2016 to 2021, 1 kilometer resolution based on Sentinel-1 soil moisture, and they are freely available. This is open data. They are available in Zenodo. We have also a product covering the Marley-Darling Basin. Here we are in Australia. In this case, the period is from 2017 to 2020, and the resolution is a bit coarser, 6 kilometers, because we used in that project Cygnus soil moisture. Here there are some metrics because we validated, of course, our products with available ground truth information, not easy to collect. In fact, in some cases like Po Basin, the validation is limited by the availability of in situ data, but we are collecting more data, and we will soon, especially for the Po Valley, we will soon release a new validation with much more data. Stuck, okay. It's too much, but this was just to show that we have other basins in Europe as an output. Previous output were from the Irrigation Plus project funded by ESA. In another ESA project for the MED, we also produced the irrigation water use datasets for Euro Basin. We are in France, and Medjerda in Tunisia. Still not validated because we don't have benchmark information, but if somebody asks, please tell us because we want to validate them. And what's new is that in a new project funded by ESA that is started kind of 6 months ago, something like that, we are working on that. We will have the whole Europe at 1 kilometer, so probably a data set that could feed also the Open Earth Monitor app and occasion for synergize. Again, in another ESA project, we have recently released the new datasets of irrigation water use for contiguous United States, Ebro Basin, Spain, Murray-Darling Basin, Australia, and India, whole country. In this case, we are working with coast resolution data, 25 kilometers resolution, but because this is a project from the family of CCI, so there is an eye on the climate perspective, so we need to create long-time series because the target is to foster climate studies. So we had to use coast resolution datasets of soil moisture. But again, the datasets are there and freely available in Zenodo. In this case, not only our algorithm was implemented, the soil moisture based in version 1, but also algorithms developed, one from TUVN, a partner of us, and also a model-based approach from Keoluvian. So also several approaches for estimating irrigation. This is an example of what we can do with these data sets, because usually when we don't have data about irrigation water use essentially. So or we estimate through satellites, or the other source is often getting model outputs. There are models that try to reconstruct irrigation water use. So we starting with, for instance, this is a work we are preparing just these days. We are comparing satellite-based irrigation water use with output from models, from multi-models, several areas of the world. And what we are finding is that when satellites and model outputs are close each other, more or less, they represent pretty good ground truth, even though collecting ground truth data of irrigation is always tricky. In cases in which there is discrepancy between satellites and models, we are observing an added value of satellites that bring an information that in principle is an observation. So it's good because it means that the irrigation signal is there. Other examples of what we do with our algorithms, this is a study of this year in which we implemented both systems, so an integrated framework of irrigation mapping and quantification at 10 meters resolution. We implemented over an agricultural district in central Italy. Here we are in the Lazio region. And again, we obtain good results, irrigation mapping, an overall accuracy of 93%, and slightly underestimates with respect to irrigation quantification, but good with respect to the scale we implemented, consortium scale and farm scale. So here we are kind of at the edge between hydrology, which is our background, and the world of agriculture, that is totally another things, but somehow with irrigation there is an overlap. Again, we did an experiment to make the system operational. So we implemented it with operational products. So Sentinel-1 from Copernicus and atmospheric forcing that we need in our algorithm from ERA5 land. And we did this in 2023, actually beginning of 2024, in Ukraine, in the area that was affected by the failure of the Kakova Dam. That was feeding a large irrigated area. So we estimated irrigation in the last 8-9 years. And what we found is, as expected, 2023 was the year with the lowest irrigation amounts yearly, for obvious reasons, because there was no more infrastructure. So a good correspondence between what we estimate from satellite and reality. And this system can be implemented with 10-day latency because just constrained by the variability of the input data. So conclusions and outlook. There are several ways to apply these products that I did not show, but that we are doing, as for instance, the assessment of the irrigation impacts on the water cycle, because once we have irrigation water use products, we can, for instance, force models, hydrological models with this data and see how the hydrological cycle is impacted, or for instance, the detection of illegal irrigation through satellite, especially with irrigation method, with irrigation mapping method is something we are trying to do. Concerning challenges, opportunities, one main challenge, which is also an opportunity, is the lack of in-situ data, because since we don't have in-situ data of irrigation, basically this is the driver of this research, because we try to use satellites for that, but we need some in-situ information to validate, otherwise we go blind. And opportunities for sure, next missions. Here I listed just a couple in the realm of soil moisture, as for instance NISAR, but for sure continuity of actually currently running missions and new ones can foster these activities. So thank you for the attention.
Thank you, Jacopo. We have time for some questions. Yes, let's see. Greg, we don't have much expertise in beyond the Lucas group in OpenNet monitoring hydrology, and
No, we trust
so
Luca.
so we are also learning. We're just learning, yeah.
So, and that's what we're doing. And in that respect, I was wondering, so you say you're missing irrigation data, like in situ, to know if what you're doing is how good it is, right? Yeah. And I was wondering about those plots, like pivot irrigation. I mean, from other satellite. I mean, this is a shape that we can really identify, and we know if we see it that for sure there's irrigation, right? So can that be an indirect way to validate? I mean, it should work there very well, right? Do you know already that, or?
Still not try to getting benchmark information from other, let's say, for instance, validate what we do with some input from satellite with other satellite information could be done. But when I was talking about lacking of in-situ data, I was especially referring to irrigation volumes.
Volumes, yeah.
Irrigation mapping, it's easier. It's easier from the technical point of view. So it's easier to map irrigation rather than quantify it. And it's also easier to get benchmark information rather than irrigation quantification.
Okay, and so maybe a side question to that, for the irrigation mapping, how good is it? Because I've seen, I mean, I think in the more climate modeling community, sometimes they use maps that seem very outdated or like very static or things like that. And I always thought, I mean, this should be doable. So I wonder, can you make a nice map of irrigation like that, like not volume, static, more static, globally or across Europe, that is quite precise? Does that exist?
In principle, yes, but we are a bit, I don't want to say struggling, but we often say to modelers to try to ingest some satellite-based information, like for instance, an updated irrigation map or an irrigation map that can change year by year or 5 year by 5 year. But often changing a chain that is already working is not so easy, but for sure it's something that should be done to me.
But the maps are ready, almost, in principle.
In principle, yes, we can do global. Yeah.
Okay. And the one for Europe, you said you are finishing
the project will finish in 6-7 months. It will be ready.
Okay.
The irrigation product.
And that's
but should be ready earlier.
1 kilometer?
1 kilometer over agricultural areas.
And temporal, is it annual?
From 2016 to last year, it's Sentinel-1 based.
Okay,
so
but it will be annual irrigation?
No, bi-weekly.
Bi-weekly, okay.
Bi-weekly irrigation.
Question, yes. Stefan, no? Who's the...
Ask so many questions. I can ask one more question.
As long as they're good, it's fine,
So I'm not an expert in this, but I know that what then also matters is the crop water requirements. So you have the irrigation, which also can be over irrigation, right? Sometimes farmers just put too much, but the crop doesn't really need it. So they say that using evapotranspiration, you can estimate with that crop water requirements. So have you thought about maybe going that step further, or have you considered that? Yeah,
in the last project I talked about, the CCI, the Climate Perspective 1, there is a team which is strong in producing irrigation water requirements estimates. And we started comparing how irrigation requirements compares with respect to irrigation water use. because actually probably a crop requires a certain amount of water, but if the farmers gives twice the amount, the requirement has a limited scope, no, somehow. And yeah, we started doing this because irrigation requirement should maybe match with irrigation water use in principle, but it's not straightforward.
Okay, we have to stop. Thank you. That
Thank
was
you.
very interesting